Chapter 5, Gas Laws. Gas in the kinetic molecular theory, the word kinetic means speed or movement. Molecular means molecule. So we're really going to be looking at how the molecules behave speed-wise, why that's important. Basic overview. We won't spend a ton of time on 5.1 and 5.2 or 5.6. The bulk should be between 5.3 and 5.5. Things we already know. 3 states of matter, and we can see the gases are far apart and they have them moving in high speeds. That's why they have the trace lines behind it. We can see the liquid is also moving, kind of random, but they're close together. The space between them is small. And we can see the solid, where there's really not a lot of movement back and forth, up and down. If there is movement, it's vibrational, and there is. But it's not quite like the liquid, and it's definitely not like the gas. But the liquid and solid are close together. All right, so things that distinguish gases from the other two. Gases are affected by pressure because, well, they're far apart. Right? And if you apply pressure to them, what happens is they go closer together. On the other hand, solids and liquids, well, they're already close together. When you apply pressure to them, they don't really go any closer together than they already are. They could, but it would take a significant amount of pressure to do so, and they're not affected as much as gas particles because it's easy to push gas particles together. Okay, gases expand to fill the container, and they're affected by temperature. Okay, so if you go ahead and you heat a gas particle, add energy to it, it picks up speed, and therefore it wants to expand even farther. And if you shrink it, you pull out the speed, you make it go slower, and it kind of shrinks. And there's a big difference between the volume change for gases compared to liquids and solids because it's all about how close they are together. Gases are extremely far apart, so if you can push them closer together, then it really cuts the volume they occupy down. They flow freely, which we already know, so do liquids. They have low densities. If you think about density, density equals mass divided by volume. We won't change the mass on a gas depending on what it is, but we can definitely change the volume. So if the volume's on the bottom and I make it bigger, then I make the density smaller. So they tend to occupy large volumes, 50 to 100 times greater, right, than a liquid or a gas of the same substance. So therefore the density should be much lower in the gas form compared to the liquid and solid forms. They always form homogeneous mixtures or solutions. Okay, so no matter what happens, when you have gases together, they form solutions. They spread out evenly. And then underneath it, they use the word miscible, which means always mixes evenly. This is our basic definition of pressure, which we won't use as much in chemistry. It's force divided by area. And if you know what force is, it's a Newton. And area is meters squared or centimeters squared, whatever that might be. So it's always the Newton divided by meters squared, which gives us a Pascal. Pascal is the SI unit for pressure. Okay? Atmospheric pressure comes from the gas particles around you. You don't feel it or notice it because you've always been in this environment with all the gas particles there, the atmospheric pressure. It's all because of gravity and its pull on the gases near the Earth. The closer it is to the surface, the greater the pull of the gases to the Earth. So therefore, the greater the air pressure. So if I go up in the atmosphere in a big mountain, it doesn't have as much pull or gravity at that point. So the gas particles should go down, and therefore you won't have as much pressure. This is a nice simple thing, and we might show this to you so you can see it. If you have a gas can that has air inside of it and you suck the air out, okay, this is what happens. Why does it happen? Well, when the gas can is just sitting there open, you have the pressure on the outside is equal to the pressure on the inside. They're in balance. If you take the gas particles out of the can, though, like we do in the second step, we suck them out, the pressure on the outside now starts to push down because there's no pressure against it on the inside. That makes the can condense. The pressure from the outside pushing on the can, which no longer has any pressure on the inside. We should probably define it at this point. Pressure in chemistry is the number of collisions of the gas particles with themselves and the sides of the container. A barometer is how we measure air pressure. And what we have is a long, thin tube and mercury inside it. We choose mercury because it's extremely cohesive, which means it sticks together very well. There are no gaps inside the tube inside of it. So we take a look and we can see a tube we have here, and we have mercury on the inside. And we have pressure due to the weight of the mercury, so that would cause it to go up the tube a little bit. But that's consistent. That doesn't change. As long as I have the same amount of mercury, pressure due to the weight of mercury doesn't change. But what does change is the pressure due to the weight of the atmosphere, because that can change. We have what we call a low pressure system or high pressure system, so that can make it rise and go down. Now, above it, we call it a vacuum. It doesn't mean it's sucking the actual mercury up the tube. What it means is there's nothing inside of it. There's no gas, there's no air, nothing like that. So the mercury is free to move up and down the tube without any hindrance from the gas in the top part. If you've ever played with a syringe and covered the end of it up and tried to push down, you can tell that you can only go so far because there's gas particles in there. In this environment, there are no gas particles, so the mercury is free to move up and down the tube. And these are manometers, and they do kind of the same thing. In this case, it's called the closed end manometer, which means the end where it says closed is sealed up. So in the beginning, we have an evacuated flask, which means there's no air inside of it. And then we put gas in the second part, and we can see how the mercury changes. The delta H is the difference in height. Delta means change in chemistry, and H means height. And we can use that to figure out the pressure due to that gas. Now this is an open-ended manometer, and so there is some atmospheric pressure pushing down on the end, so there should be some resistance, but not enough to make much difference. We're not going to worry about it. So if we have a gas on the inside in the beginning, right, and we have pressure pushing down on it, the greater the gas pushes on the mercury, the more that it'll go ahead and increase or move the mercury up the tube and increase the pressure there. We're not doing anything with manometers. So these are our common units of pressure. Pascal is the SI, or actually kilopascal is the SI unit. ATMs is the normal one because, well, it says 1 ATM there. Do you see that? Millimeters of mercury and torr are the exact same thing. Bar is also used for what millimeters of mercury because it's in a barometer, and torr, they're used for atmospheric pressure or weather, usually. And then pounds per square inch is things we inflate. The United States likes to use pounds per square inch. It's definitely an English system. And it's based on the fact you have a force, which is weight, divided by an area squared, which in this case is inches. Or area squared. Area, which is in length times width. And these are all equivalent. So that means 1 ATM equals 101.325 kPa, which equals 760 millimeters of mercury, which equals 14.7 pounds per square inch, which equals 101.325 bar. Those all mean the same thing. So they're conversion factors. We're not doing this. Okay. And I might not do that at all, actually. So when we describe gases, we like to use 4 different things to do so because they're consistent, they're patterns. Pressure, which is collisions. Temperature, which is the speed of the molecules. Volume, which is the space occupied. And amount, which is the total number. So when we talk about these, pressures should be in either one of 2 things, kilopascals or ATMs. Temperature should be in Kelvin. That's important. We never use Celsius because Celsius can be negative. We need something that can never be negative, so it's based on absolute zero, so it's Kelvin, never negative. Kelvin is never negative, and we get that way, which we'll show you later. 273.15 plus Celsius gives you Kelvin. So negative 273.15 degrees Celsius is what we call absolute zero. It's an equivalent to 0 Kelvin. Volume we measured in, well, when we do the ideal gas, all liters, but it just depends on what units we have in the problem we're dealing with. An ideal gas, something that always behaves like a gas. Most gases will behave ideally as long as you're not starting to turn into their liquid phase. And so the easiest way for them not to turn in liquid phase is to keep the temperature high so they're moving crazy so their attractive forces can't take over, and let them move away from each other, which means decrease the pressure. There is no actual ideal gas, but things like helium and hydrogen are very small. They have a few number of electrons. So what tends to happen is they don't have very strong, we call London dispersion forces. I know we don't remember that stuff because it's been a while. But attractive forces are a big thing. In London dispersion or attractive forces, they're forces between two different molecules, and how drawn to each other they are. So that's why gases don't behave ideally, because there is some attractive force between them. But the ones that do behave closest to it are small, so they have the weakest attractive forces. And this shows Boyle's relationship. What we have here is, as I increase the volume, I decrease the pressure. So if I make the container bigger and I keep the temperature consistent, the same, so the speed that they're moving at stays the same, then the total number of collisions in the system should drop. That's Boyle's law. And it kind of makes sense, because if you have gas in the container and they're moving at a certain speed and then you double the size of the container, well, you're not going to have the same number of collisions anymore because there's more places for the gas particles to move. And it shows an inverse relation between pressure and volume. As long as we keep temperature and amount the same. And inverse means as one goes up, the other goes down. This is Charles' law. And Charles' law is what we call a direct relationship between the two. And the key thing here is to keep the pressure constant. You have to keep the number of collisions the same. So if I have something within a certain container, certain size, let's call it a liter, and I take the particles and I make them move faster, as long as I don't change the size of the container, then I should have more collisions. They're moving faster in the same space. More collisions. So in order to keep and the pressure goes up. So in order to keep the pressure the same, and that's collisions, pressure is collisions, then we need to go ahead and make the room bigger so the number of collisions are the same. So temperature and volume of a gas are directly proportional. And that's what this shows. Okay. As one goes up, so does the other. It's about maintaining the number of collisions. There's actually a third one that I don't know why they don't mention here. It's called Gay-Lussac's. And in that scenario, it's the pressure and the temperature that are directly proportional. So in Gay-Lussac's, pressure and temperature are directly proportional. Now, later on, I'll show you an equation that we can use, and we'll use it for all of them. And this shows a relationship between, it's called Avogadro's law, and it's about the number of particles inside the system and the volume it occupies. So I keep the temperature and pressure the same. So the speed of the molecule stays the same and the number of collisions is the same. If I go ahead and add more particles, then I have to make the room bigger so the number of collisions stays the same. So with Avogadro's law, it's the number of particles, the moles, is directly proportional to the volume, as long as temperature and pressure are the same. I don't know why this is here, but it's a cool picture. Now, a lot of times we like to study things under specific conditions, come up with numbers and verify. So an ideal situation or a good situation for us is to study gas behavior at 1 atm and 0 degrees Celsius. So we call that STP. how we like to run reactions in that situation. And at STP, 1 mole of any gas should be equal to right around 22.4 liters. Okay, at STP, that's what it is. So this is also a conversion factor. 1 mole equals 22.4 liters. And here we have 3 different gases, very different, all non-polar, that part's the same, but different weights on each one of these, and they're going up as we go across the table. And we can see that the volume, as long as we keep the temperature and pressure at STP, should be 22.4, and it is. The number of gas particles is the same. So 1 mole of any gas at this temperature and pressure should give us the same number of 6.022 times 10 to the 23rd particles. And there's range in densities, but they should be small. Although nitrogen seems a lot more dense than the helium. And it just shows some different things. Probably should get rid of that thing. Okay, so this is the equation we want to use. There's 2 different ones on this page, and both are important. PV equals nRT is the ideal gas law. Okay? So in this situation, we don't have changing conditions. We have the pressure, volume, amount, and temperature at specific times. And so we go ahead and we run it. Now at 1 ATM and 22.4 liters, and 1 mole at standard pressure, we get our R value. R is what we call the universal gas constant, which means it always stays the same. And we're going to use 2 different values, which sounds strange. It always stays the same. We're going to use 2 different values. And our value is going to be based on pressure. So one is on the screen, 0.0821 ATMs times liters divided by moles times Kelvin. But if we're using the SI one, then we'd end up with kilopascals. So it'd be 8.314 kPa times liters divided by moles times Kelvin. And so it just depends on what the pressure unit is. Underneath, we can rewrite it, and it's another way to express it, which we're not worried about how we got from point A to point B at this point. And so this is a combined gas law. And what's nice about this is I can get it to show certain things. If we cover the bottom 2 up, the N1 and T1 up, and N2 and T2 up, we cover those up, then we end up with P1, V1 equals P2, V2. By covering up, I make them constant. So the N1, the amount of moles become constant, and the temperature is constant. Then I cover them up, and I end up with P1, V1 equals P2, V2, which is Boyle's law. So this gives us all of our other laws. We just cover up the ones that are constant. Another example is if I want Charles, that's volume and temperature. If I keep the pressure and the amount constant, then V1 over T1 is equal to a V2 over T2. And we'll play with this equation in class. All right, and this is everything spelled out for us, the ideal gas law, and we'll do a lab on the ideal gas law. That's what we're really looking at. And it has all the laws inside of it. Lots of problems. Holy cow, what happened to 5.5? I gotta figure out what happened. Now we can bring density into it as well, in the ideal gas law. And because we know that density is equal to mass divided by volume, and moles are equal to mass divided by molar mass, we can kind of substitute in for N, M, mass divided by molar mass. And we can solve for molar mass, obviously, right? And we can also solve for density. Density is equal to molar mass times pressure divided by RT. And it's just a different way to manipulate the ideal gas law. And here's another, solving for molar mass of a gas. Little m stands for mass, and the italic m stands for molar mass, which you usually get from the periodic table, but you can also solve for it here. Okay, and we said this already, the gases mix homogeneously, we call them solutions. They're completely miscible. It's just how they are, and they behave as if they're the only gas there. They're totally independent of each other. So when we have multiple gases inside a container, we can solve for the pressure of each gas independently, and that's what we call the partial pressure of that gas. Now, Dalton's law says that inside the container, if I have like 4 gases, and I can figure out each one's individual or partial pressure, Then if I add them up, I should get the total pressure of the system. So it's not on here, but it's usually P total equals P1 plus P2 plus P3 plus P4 and whatever on how many gases might be in the container. Now this is a different way to do it on the bottom. We want to find the pressure in an individual gas. X stands for what we call the mole fraction. And mole fraction is kind of like a percent. We look here, we can see that if we take the mole of the gas we're trying to study, divided by the total number of moles, then we get the mole fraction. The mole fraction, right? And so we go ahead and we take the mole fraction, we don't multiply by 100, we multiply by the total pressure in the gas. That gives us the partial pressure, individual pressure of that gas based on the number of moles it is. Okay, so a lot of times what we'll do is run experiments with water. And why we use water is because we take a container like this one here on the screen on the left-hand side, and what we'll do is we'll fill it completely with water. We'll flip it normal, we'll fill it completely with water. And what that does is the water pushes all the gas out of the tube, so there's no gas in the tube whatsoever. And then we'll flip it upside down, we'll insert a tube inside of it, and we'll run a chemical reaction that produces a gas, like this one. And what the gas will do is it'll go ahead and push the water as it's being formed, goes through the tube and goes into the test tube we're at, the upside down test tube. It'll collect at the top and push the actual water out of the tube. That's how we know we get just the gas of the one we're studying, what we want to produce. Now, that pesky water, on some levels it's awesome, other levels it's not. So if we look at the bottom on the right-hand side, we can see the total pressure is equal to the pressure of the gas we made, which is orange, added to the pressure of the H2O that was actually gone and formed, because water, how great it is, it turns into a gas right at room temperature, right? It's called humidity. And so on some level, some of the gas inside this tube, some of the pressure is due to the water vapor that's actually evaporated, just because water is part of the process. So there's a way to get away from that, though. If we go to the next page, they've solved for the water pressure at different temperatures. So what we would do is we would take the pressure, whatever the temperature of the situation was, we find its water pressure on the chart on the next page. We subtract it from the total pressure, and we would get the pressure just to the gas. Now, the pressure, total pressure before we take the water out is called wet gas. And after we remove the water, after we subtract the pressure due to H2O, the gas is left over, we call it a dry gas. And here are all the ways that we can involve stoichiometry, right? Awesome. With the ideal gas law. So that means at some point in time we're solving for mole. Because mole is what stoichiometry is all about. And the ideal gas law gives us the number of mole. So the two are related. All right, the kinetic molecular theory is so that we can use the ideal gas law. Sometimes this is like 5, 6 different postulates. Here they've combined a lot of them, which is fine. All right, some things we have, right, that we already know. Gas particles have large spaces between them. What they're also saying is the gas particles individually are just so small that we assume their volume to be 0. That's kind of a big thing, right? Two constant random straight line motion, they collide with each other, right? And with the container walls, that's what creates the pressure. So they're moving straight until they run into something, and then they bounce and become something else, right? Collisions are elastic, okay, which means when they run into each other, no energy is lost, okay? But the total energy is constant. So if I have 2 molecules, gas particles, and one's moving at 5 miles per hour, and the other's moving at 6 miles per hour, and they run into each other, and now one's running at 3 miles per hour, the other has to be moving at 8, the total is 11. So that's what they mean by elastic. Total energy remains the same. Even though the speed of the molecules might change and their kinetic energy might change, the total together, right, should be the same. And the last part, which is probably the most important part, and they kind of threw it on here at the end, which is kind of weird, It can be its own postulate. Gas particles are not affected by attractive forces at all, or repulsive, but really attractive forces more than anything else, which we know is not true, right? And which kind of messes things up a little bit, because when they're too attracted to each other, then what happens is they turn into a liquid. And really, states of matter are based on two things. If it's a solid or a liquid or a gas, it's all based on two things. It's kind of a fight between the two of them. How fast the molecules are moving and how strong the attractive forces are. If I go ahead and I slow them down, then the attractive forces take over. Or another way to do it is if I go ahead and forget about making them move slower or faster, if I just push them closer together, attractive force will take over. That's called pressure. A very common map, graph. And what we show is at different speeds, right? Different gas particles, the same gas particles at different speeds using nitrogen. And we can see how the the chart changes. What happens is if the slower the speed they move at, the less range of temperatures we have. So the blue one represents a lower speed, 273, which is 0 degrees Celsius. So most of them fall into that large curve underneath the blue, right? Especially the line. That's the most probable speed, right? And if we remember that temperature is the average kinetic energy, then it can be any of those speeds underneath there, but most of them fall into that bracket. And as I make the temperature go up, the speed goes up, and there's more speeds. And there's more speeds for the gases to move at. So then we end up with a wider curve. And here's how they show that we end up with pressure, which is collisions with the sides of the container themselves. In Boyle's law, basically, we exert pressure on the gas, and the volume goes down. We keep the temperature, right, so not moving any faster, and the amount of particles the same. And here's Dalton's law. It has two gases individually, and we go ahead and put them together, and it becomes the total pressure of the gases. And here's Charles' law. With Charles' law, the big thing is you got to keep the number of collisions the same. Okay, so in the first one, we have a certain temperature moving around, and then we increase the temperature. So what does the volume do? Well, in order to keep the number of the pressure the same, you have to make the container get bigger. Otherwise, we get more collisions because they're moving faster, so the pressure should go up. Okay, and here's Avogadro's law. We put more particles inside the system. In order to keep the pressure the same, number of collisions the same, we have to give the molecules more space, even if we don't change the temperature. Okay, so at a given temperature, all gas and sample the same average kinetic energy. Average is the key word. The kinetic energy is equal to 1/2 the mass times the speed squared. Essentially what it's telling me is if I have two gases at the same temperature, let's say that I have hydrogen and carbon dioxide. Hydrogen is a small gas, so it has a small mass. Okay? And carbon dioxide is a large gas, so it's a big mass. So in order for them to have the same kinetic energy, there has to be a difference in speed too. So the heavier molecule moves slower, and the smaller molecule moves faster. And then stated in the bottom, the same temperature, a heavier gas moves slower than a lighter one. It's all based on that equation right there. Okay, and again, what happens when we have a heavier gas? We have a shorter range of speed we can actually work with, because, well, they're heavier, so they're moving slower, right? So the speed is smaller. So we end up with the red line being taller. And then hydrogen is so small that there's a wider range where the speeds can be at because the mass is so small. Okay. There's two things that go with this. Graham's law of effusion, diffusion, they kind of go together. But effusion is this. You take a can that's highly pressured. I used to think of like hairspray cans, metal ones. And you go ahead and you poke a hole in the bottom of it. It makes a loud noise, boom, right? Because all the gas particles inside the can are under high pressure. That's why it works when you press the top, right? You open it up and all the gas particles come out. That's effusion right there. But anyways, So you go ahead and you have a can full of a gas and you poke a hole in the bottom of it with a nail. And what happens is the gas leaves. That's called diffusion. It's the escaping of the gas through the hole. Okay? That's an easy way to think about it. And so what happens is when you poke a hole in it, the gas comes out so fast that it pushes all the air that's on the outside of the can away from the outside of the can. So now the gas that's still inside the can can come out without anything interfering with it. That's what diffusion is. And again, it's all based on a lighter gas, right? The lighter the gas, the faster it moves. And it has this relationship here, 1 over the square root of the molar mass. And there's actually an equation which we'll deal with in a little bit. Okay, so it's diffusion. And here we have a container with a hole in it, and they're kind of escaping. All right, so there's high pressure on one side, and it wants to go to the other side. It's something called equilibrium, right, where things like to be equal. So if it's high pressure, it always wants to go to low pressure. So if you open up the can, it always wants to come out. So it can be the same. And here we show diffusion. Diffusion is a little bit different than effusion, because diffusion means you have a bottle of perfume, you open up the can, open up the bottle, and you let the gas spread out slowly through the room. Unlike effusion, where the gas particles on the outside of the can are blown out to start with, so the gas can escape without anything being in the way, diffusion always has other particles in the way. So we end up with this kind of meandering movement. We can still apply the Graham's law here, but it's not quite as accurate because of the fact there are gas particles blocking the molecule from moving one side or the other, so it's affecting what's happening. I like the picture, I just don't know why we're worried about it, okay? And this shows the atmospheric pressure, or sorry, this shows the components of the atmosphere, the different gases that make up the atmosphere. 78% nitrogen. So when we think of air, we really talk about nitrogen because it's so much of it. So 28 grams per mole. And so when we compare things to it, that 28 grams per mole, if it's smaller than 28 grams, then we say it's lighter than air. And if it's heavier than 28 grams, we say it's heavier than air. So heavy gases tend to be heavier than nitrogen. There's all kinds of good stuff in the air. All right, now, real gases are a little bit different than ideal, and just a little bit. But in this level, we want to make sure we make the correction. Here's the big thing that we deal with. Gases are attracted to each other. Okay, that's kind of a problem when we're describing how they should behave. Because if they're attracted to each other, then they'll clump together, and then they'll turn into liquids at certain temperatures. So that's kind of a problem for ideal gases. But we can assume most of the time they do behave that way, right? And also they have space. They occupy rooms, so they're in the way of other things, so they cause problems. So real gases deviate, and this is probably the important part of the bottom, most from ideal behavior when the temperature's low, so they're moving slow, and they're under high pressure, so they're pushed closer together. In effect, what the difference is, those two things mean that the attractive forces matter more than when they do when they're high temperature. They're spazzing out and they're no longer attracted to each other really, and then they're low pressure where they can space out as far as they want to be. So it's all based on attractive forces. Low temperature and high pressure favor attractive forces. And we calculate the real molar volume, 1 mole at STP for all these kind of things on here. And we can see that they're all still pretty close. The Cl2 and NH3, they start to get a little bit too much attractive forces going on there, and they don't behave as ideally as they should. But the helium and hydrogen and neon, they tend to do exactly what they're supposed to do. Gives a different boiling point. This shows you how attracted they are to each other. The boiling point tells you how attracted they are. So what this one means is that negative 268.9 liquid helium turns into gas helium. Well, absolute zero is negative 273.15. So that happens like 4 degrees above absolute zero. Every other temperature after negative 268.9, and really almost every pressure, helium is a gas. Okay, and this shows our change from the ideal behavior. We want a straight line. We like when they're straight, that's ideal. we can see the hydrogen and the helium pretty much behave ideally on a lot of levels. Because they're straight lines, but they deviate a little bit. And it's all based on how attracted they are to each other. Okay, and we can see that it knocks down the number of collisions if they're attracted to each other, not significantly. It's not going to make a normal view of things. We can see in the last picture, though, they are attracted to each other. That causes some issues. Okay, and the space they occupy. Okay, so this is our correction. And on the page you have, right here, the ideal gas law. And so this is our correction for it. A is for the attractive forces, and B is for the volume. And you don't have to know those numbers. They'll be given to you. But the significance is we have to factor them in when we do this stuff. So this is still the ideal gas law with a correction for the attractive force in A and for the volume in B. And here are some values which you do not have to memorize. They call them van der Waals because van der Waals is really the attractive forces. So we dealt with attractive forces, London dispersion really. Okay?